My name is Ashish Chowdhury, and no, I did not wander off into the wrong conference. I am about to talk about audio effects. I realize this is a radio conference, but just to give you some background, I do work in radios as my day job. So more specifically, I build software and FPGA code for USERPs, the tech lead for RF NOC. So a lot of work I do sort of dabbles in computer architecture, DSP, more applied to the RF. But as a hobby, I'm quite a music enthusiast, and I really like producing electronic music, which, by the way, is making music out of DSP, which is super nerdy and awesome. And this is sort of my attempt to bridge the two audio and RF worlds together. So just deconstructing the title here really quick. It's really long. And the way I would read this is, starting with the dark side of DSP, which I define as signal processing phenomena that most communication RF engineers try to avoid, things that people don't like in RF. We take that, and we embrace them to make some cool audio effects. So hopefully, I'll sort of bridge the two worlds, and it'll be somewhat of an entertaining experience. Cool. So with that, I'll kind of jump into the outline. I'll talk about just generally audio DSP, how it's somewhat different from RF, or not really. And then I'll cover two different effects, the wah-wah guitar effect and the distortion guitar effect, and sort of do a whole yin and yang thing where both of those are based on things that we don't like as RF engineers, and sort of what other takeaways are. We listen from 20 hertz to 20,000 hertz, and these are kind of the main bands. Pay attention to the mid-range band, the 250 to 4 kilohertz band, which is where most of the sound is perceived. Voice is in there. If you have a musical instrument, its primary harmonics are in that range. And then you have the high-frequency stuff that gives your sound some amount of character, sparkle, as they define it. So that's frequency. I was just talking, and it's logarithmic. And I was talking about amplitude. So I'll start over on this slide. So amplitude is sort of a measure of sound pressure level that your ear is experiencing. And dBSPL is typically how audio engineers refer to amplitude. And usually they colloquially just use dB for it. So if I use the terms interchangeably, I really mean dBSPL. And so that is logarithmic as well. And the projector died. Is it just this slide that it dies on? You're still good? Yeah, is that the slide, really? What the hell? Okay, that's fine. I'll skip that slide. Let's see. Oh. Okay, I promise there are no rootkits here that are getting transmitted over HDMI. Okay, anyway, so
actually, we're still missing it on the far left side.
Okay.
So whatever rootkit you installed.
Yeah, I know. Accidental black hat presentation.
All right.
Okay, so I'll describe what was on the previous slide. Basically, I had contours. So dBSPL, 0 dBSPL is defined as your threshold of hearing. It's what you will barely hear. And then you have sort of whispers of sound in the 15 to 20 range. You have actual voice in the 50, 60 dB range. And you have like pain threshold, which is where your ears physically start to hurt, is around 130 dBSPL. So our ears have a really amazing dynamic range when it comes to perceiving audio. And that's what makes audio a little more interesting. That's why you'll see sort of 24 bits for audio ADCs and DACs than the typical 16 bits. And the cool thing about audio is there's a little graph that I will describe, is you have loudness curves where at the low frequency, you perceive loudness at a much higher level than at high frequency, because our ears are optimized to amplify human sounds, especially high-frequency human sounds, evolutionarily, and we sort of take advantage of that in audio DSP quite a lot. So as a previous slide, this slide is, so is it really different from RF? Well, fundamentally, no. If you just change the FS on a particular algorithm, it doesn't really change the actual DSP. The differences are in sample rates. So it's in kilohertz. So 44.1 is sort of typically what your standard laptop audio card has. 48 is getting a little high. 96.192 is mostly sort of studio quality production level. Probably you will never actually use those sample rates in normal audio. And the thing that makes it different is human perception drives filter design. Not spectral efficiency, not hitting a particular spec, it's how it sounds. So filter may look completely weird to you on a slide, but it sounds really good, and that's what drives audio design. And another thing that you didn't see in the last slide is frequency axes are usually in log in a lot of audio plots, which is a little different. And it's hard for us to hear phase. And by phase, I mean if there's a distant source that's playing a sine wave and it's changing the phase, you can't hear it. If you play the same sound source with one phase in one ear and another phase in another ear, you will definitely hear it. So from a non-stereo sense, you can't really hear phase, and we take advantage of that in audio design. And that's why a lot of audio DSP actually happens in the frequency domain. You go from time domain, FFT, do all of your signal chains in the frequency domain and back down to time domain. Makes it easier. OK, so that's sort of general primer of why audio is a little different. So I'll jump into the first effect. And this is where we'll see the yin-yang thing going on. We will talk about filter resonance and how that breeds the wah effect. So what's resonance? So it's the tendency for a physical system to oscillate at high amplitudes at very specific frequencies. So you've probably heard of resonance in sort of the control systems type of environments, but it actually comes from acoustics. Like if you look at the root of the Latin root of the word, it comes from acoustics. And inherently, resonance isn't bad. You can make some really interesting things by making things resonate at a particular frequency, RCLC type of things, basic circuits. But typically, when you're designing, say, a filter, if you have that, you'll try to get rid of that peak, right? That has a lot of nasty effects. If you're a structural engineer, that peak is what's going to make your bridge collapse. If you're doing any sort of control system stability analysis, those peaks are usually kind of not wanted. So what do? We apply damping. So we damp that resonant peak and make it nice and flat again. And in a wah-wah effect, we do the opposite. We build a filter. We try to amplify the resonant peak so that it sounds kind of weird. And here's the Wikipedia definition of wah-wah, which is way too wordy. It sounds like wah-wah. That's the effect. And here's the sort of DSP academic definition of a wah-wah effect. So it's an effect that sweeps the cutoff frequency of a resonant digital state variable filter and produces a spectral glide. So a bunch of terms that I threw in there. We'll start, and by the way, that's sort of the quintessential Jimi Hendrix sound, if you guys like Jimi Hendrix. That's not a stapler, that's a pedal for wah. It's called Crybaby for obvious reasons. So state variable filter. What is that? It's just a series of integrators feeding back and forming a filter by summation. And there's sort of nothing special about the filter in terms of properties. The state variable comes from its representation, which is in the state space model. So this is what it looks like in the continuous time domain. It's a very simple 2-tab Butterworth filter. I have 2 forward integrators. They each have a feedback term that adds back. We take the input, it produces the output. And you have some weights on the feedback terms. And note that this is in continuous time domain. And also note that we have 3 outputs here. while this is a low-pass filter, the cool thing about the state space representation is you usually have your state space matrix, which is a linear function of your state, the derivative of the state, the nth derivative. And if you look here, the band-pass output of this filter comes from this tap, and the high-pass output comes from this tap. So this filter is giving you 3 different properties in a single structure, which is quite nice, which we can use. And why am I talking about continuous time? It's because that's how they built it when they first introduced the wah pedal. You can see the RC integrator here, which maps to this one, another RC integrator here, and a summing amplifier. And you have the 3 outputs right there. But for doing DSP, we need to digitize this. Typically, the easiest way to do this is using a bilinear transform, but that would give you a 0 delay feedback, which is bad. So what we do is we take this. Oh, by the way, I just wrote down the transfer function of this, and we normalize the S to the cutoff frequency, and we apply damping, which is basically just square root of 2, that term, just the math. So how do we digitize this? Well, we apply forward Euler on that first integrator, and then a backward Euler on the second integrator. That gets rid of the 0 delay feedback, but it still gives you a bunch of pretty balanced digitization. And if I do the Z transform or the discrete model, that's what it sort of maps to. You'll see the forward Euler show up here, where you have the delay in the feed-forward path with the scaling for frequency, and then the backward Euler is the feedback in the backward path, and of course the sum. So what we just built is 3 filters at the same time: high pass, band pass, low pass, using 1, 2, 3 multipliers and 4 adders that we can use for our effect. It's pretty cool. And since this is IAR, hey, we don't care about phase linearity. It's really efficient to implement. OK, so that's a digital state variable filter. How do you build the effect from it? Well, we take a linear combination of 2 of those outputs. I chose band pass and low pass. You can sort of play around with different ones with different weightings. And we just take the cutoff frequency and vary it over time. And it gives you the effect. It looks something like this. So the various traces are different damping levels. This is a band pass output only. If I go easy on the damping, I get this nice little resonant peak. If not, I get this flat peak. The resonant peak is what gives your wah the sound. So as you see that move around, you'll have a couple of questions. Hey, why is the bandwidth of my filter changing as it's sweeping? OK? That's because we hear in log. My frequency axis is linear. If I translate that axis to log, the bandwidth is now quite nice. Looks weird in the linear frequency model, but that is what we hear. And also, you'll see the amplitude is changing. Well, that's just kind of the side effect of the filter design. But it works out that if you target the start and stop frequency in a certain range, you're sort of riding the contour that our ear listens to in terms of loudness. So the perceived loudness of this fade is indistinguishable from one point to the other. So it just kind of works out. And it's a nice little efficient implementation of the filter. So enough talking. I'll do a quick demo here. And I wrote a little out-of-tree module with it's called GR and the wah-wah filter is just a block. It's still there, good. OK, so I will mute and start this up. So I'll just visually describe what you're seeing here. You have the original signal, which is with a guitar sound, the wah signal. I have some waterfall plots here. I'll let them prime up. And here, the effect is off right now. We have our damping Q number here. I'm just describing so as I move around, you know what I'm doing. You have the min and max cutoff frequency. Those are the bounds for your sweep. You have we have a low frequency oscillator in the block that is driving the cutoff frequency. So the frequency is taking a sinusoidal envelope. And we have a gain. It's kind of just there. So. Okay. Thank you. I have more. So you can take the LFO and replace it with an external signal. That was that stapler pedal that I talked about. Usually, Jimi Hendrix didn't have an LFO. He manually controlled the frequency. So why not do that? So in this flow graph, I have my input signal. I do very coarse low-pass filtering of the input signal and drive that as the I'll drive that as the envelope for the frequency. There you go. For the frequency glide, and we'll see what happens then. So again, I'll describe what you're seeing here. Min-max cutoff frequency, same thing, damping. Envelope gain is how much I gain that little low-pass filtered signal to exaggerate the effect or not. And you can see the envelope right next to the blue trace, right? So. Subtle, but you can see every time he strums really hard, the frequency goes up because it's tracking, the frequency is tracking the amplitude envelope. I can exaggerate it. This is a little harder to hear than the last one. Okay, the reason it's hard is because damping is quite low. Hey, it's not a resonant filter anymore. Notice how it sounds more steely and kind of metallic. That's sort of frequencies in the high above 4 kilohertz range. Nothing to do with the effect, just what happens. That's the raw. So yeah, there you go. That's your wow effect. And you can drive arbitrary signals in there to make it sound interesting. Okay, so I'll go to the next one, which is distortion. So again, the bad thing in DS, the dark side, is non-linearity, and that gives you the distortion effect. Luckily, I don't have to talk much about non-linearity. Oh, my slides went away again. But the title says, do we care about non-linearity? And the next build says, yes, all the time. And we come across non-linearity in, say, power amplifiers, where you want to drive them as efficiently as possible. So you drive them in that little shoulder nonlinear range, and you do really complicated stuff like digital pre-distortion to actually make them linear, so nonlinear to linear. You have to work around nonlinearity in pretty much every RF design in terms of calibration. We prefer FIR filters, phase is linear. So plenty of places where we try to remove or avoid nonlinearity. And that's sort of the takeaway. We go through a lot of work to go from nonlinear to linear. But with distortion, we go the other way. We have a nice little linear signal, and we say, I'm going to butcher you with a nonlinearity. And that's kind of the definition of that effect. And this is sort of the technical definition where we boost the input signal. So we apply some sort of gain, and we apply some nonlinear function to it to pretty much drive it into clipping. And then we may post-filter it after that. And typically, it's in rock. I'm sure everyone's heard a distorted guitar here. It's sort of a typical guitar that would produce a sound like this. The guitar gets the credit because of the badass look, but it's that little orange pedal that's doing most of the work there. So, to the underappreciated. All right, so clipping functions. How do we apply clipping? This is probably the most simple way of doing that. What you're looking at is a graph where the x-axis is the input amplitude, the y-axis is the output amplitude, and it's nice and linear with a slope of 1. As soon as you go above 1, you clip. It's a hard clip. Typically, your sound doesn't go past plus and minus 1, so you have to sort of force it into that range by boosting it, or the boost is the distortion term, but gaining the signal, right? You apply gain of 2 in this case, it squishes the curve, and now you hit your clipping much quicker. And there are multiple ways of doing the clipping too. So you can do a soft clip where you're slowly approaching your clip level, so you don't have as much frequency content. This little knee where the second derivative is not 0, it adds more frequency content. The soft clip is nice and soft. You can also do sort of a combination of the two. It's somewhat soft because the slope approaching the clip is low, but it's still kind of a hard clip. This gives you like a nice fuzzy sound, again in that high frequency range, 6 to 20 kilohertz, which sometimes you prefer. So that's kind of what clipping, hard and soft clipping looks like. I'm throwing in a half amplitude sine in, and my boost here is 3. The hard clip just clips right discontinuously, or not, the derivative is discontinuous. The soft is nice and rounded. And it's quite easy to see that in the spectral domain. The hard clip has a lot more frequency content, soft clip doesn't. Sometimes you want it because you want your guitar to sound gritty, sometimes you don't, so you have some choice there. And that's pretty much the same slide, and you have a gain and a nonlinearity, but you can oversample to remove some of the unwanted harmonics. This crap of harmonics here doesn't sound good to the ear because it resembles white noise. So if you have a non-oversampled clipped waveform, you'll hear like literally noise, white noise in the background. And that makes it sound not as good. So you interpolate, then you apply the nonlinearity with the boost, and then you decimate again. You still have the harmonics, because that's what we want. That's what the distortion effect is. But it's cleaned up a little bit. And in soft clip, it's cleaned up quite a bit. And then after you've non-linearized it, you can do some sort of filtering afterwards to give it, again, character. Typically, if you have a rhythm guitar, you want to boost the low frequencies. If you have a string sort of metal guitar, like a lead guitar, you want to boost the high frequencies. And because your signal is such rich in spectral content, these filters go a long way to define the character of the sound. And we use shelving filters to do that because we don't want a straight low-pass filter with high, strong cutoff because it completely removes the other whatever is not in your passband. Shelving filters are sort of more gradual. They will gently boost or cut a particular frequency band. And you can string those together. In my example, I only have one, but you can put a lot of these together. So there's the full chain. So you have some input, you do interpolation, and I created this interpolating IR filter block because I have this really sharp elliptic filter with like 5 feet forward, 5 feet back taps that gives you really nice rejection, but we don't hear the phase, so it works out. And there's some gain compensation or distortion, and again, a decimating IR filter, which does the same thing, same taps, and we have a shelving filter and an audio sync. So, brings us to the demo. I will mute again. Okay, similar deal. This is your original signal, distorted signal. We have a clipping function that we can choose from. We can select our boost value. That's our pre-gain. I have a shelving filter that's a low-pass filter. And the cutoff is moving the frequency of that filter. And we have a wet-dry mix. Typically, you have that in distortion. You don't want to play just the distorted sound. You want a linear combination of your distorted sound and your clean sound. Otherwise, it sounds pretty bad. So 50-50 is good for now. So that's the clean sound. Can you guys still hear me? Yeah. All right. I have the sign non-linearity on. I'll just turn on the effect. Subtle. Change the sound a little bit. My boost is not that high. So I gain the signal by 10x. Check out the distorted waveform. This is completely unrecognizable. But if I look at the spectrum, it's still there. It has most of the content of the signal, mostly because we're adding high frequency noise. We're adding more high frequency content outside the band that we typically don't hear, like outside of 5 kilohertz. So the waveform looks like garbage, but we can still hear it. It's pretty interesting. And the different functions are a little hard to hear without headphones because you have some high frequency content, but maybe you can hear it. But it does make a difference. The hard versus soft clip does make a difference. I'll move around the shelving filter frequency so you can hear the character that it's adding. It's more of a lead guitar sound. This is more of a rhythm guitar sound. Backing guitar, just based on a particular filter cutoff frequency. Yeah, so, and that's what the clean thing sounds like. So that's distortion for you. All right, so as I close the talk here, why do we care? They're just kind of toy guitar effects. We care because they have some educational value. So my background is in computer architecture. I do not have any formal training in DSP, but this is how I learned my DSP, by playing around with audio. And it was exciting because I liked it, but it's also sort of easy to grasp, easy to perceive. The effects are not complicated. Like you saw the filter structures, the decimation, the wah, the non-linearity. They're pretty fundamental, but they convey a lot about DSP. You can learn a lot from just those. So it's easy to present it in an educational setting. And that's why I'm here. Implementing in GNU Radio was super easy. I just fired up GRMod tool. I first started with a Python block. and had distortion wah blocks, put them together. After I did the interpolation, it didn't actually work in real time, I'm guessing because of the Python. But then I said, OK, whatever, I'll just do it in C++. More blocks, and it took me, I don't know, a couple of days to implement all the filters, on and off. So it was and most of my focus was on the actual DSP, not, hey, do I need to worry about buffers and whatnot, which I do in my day job. So it was a nice little break from that. And yeah, so it was also a very easy transition from simulation to actual deployment, right, hardware. So the only hardware I need is my sound card, and hey, I just graduated from simulation. So overall, it's really easy to teach. It's really easy to learn DSP when you can perceive it and when you can hear it. That's how I learned it. So hopefully, it helps someone else, hopefully. And that's where the out-of-tree module lives, and that's all I have. Any questions?
Hi, I'm curious, were you playing through an audio file, or were you actually playing real time with microphone input, or maybe even more advanced, better sound quality inputs?
Are you asking how the format affects the sound quality?
Yes. Because you mentioned you graduated into C++ for real-time processing. If you were just playing with a saved file on your computer, then you can take your time, basically. But if you are actually playing real-time recording.
Yeah, my demos were supposed to be where I come up here and play the guitar, and you can hear it. But I didn't want to do that because I suck at playing the guitar. So that's why I have the audio files. But you're right. Yeah, if you have a file and you're post-processing it, you still have the DAC on the other side, right? You still have the sound card that has to accept input in real time. But yeah, you can post-process it, throw it into a file, and do that. Yeah.
Any more questions?
Sort of be right on the other side, sorry. Thank you. Thanks. I just wonder, in the audio industry or the music industry, they must have lots of people that do this kind of thing. Do they do this? Is it digital? Is it analog? Is it? Has there been any interest, or do you think there'd be any market for this kind of thing with, say, independent bands or music studios or production companies, something like that?
Yeah, so this is definitely done in the audio industry, and the effects I showed are pretty basic. Like the DSP that they employ there is a little more complicated. And it's funny that you mentioned audio versus digital. The audio enthusiasts always want to go analog. Like, I want my digital effect to sound more analog. I want it to sound like this cabinet I had 50 years ago. And there are companies like Universal Audio, and they have product lines dedicated just to have DSP that emulates analog signal processing. So it's a pretty interesting interesting market in that sense, where.
Awesome talk. I do this sort of stuff on my signal processing course myself, and I never go to this much detail. I mean, you've went to in very explicit detail on all of these things. I really like your talk.
Thank you.
Delay. How much delay is there between microphone and going in, signal going in, and
I haven't actually
signal going out?
that.
Can you play a guitar? I mean, 'cause I really can't. My implementation is Python, and it takes like 0.1 seconds.
Yeah. So I haven't actually looked at the delay. I haven't tried.
Maybe with
did
C++.
this 2 weeks ago.
Maybe there's some GNU radio setting that would allow you to reduce the.
Yeah, I'm sure
delay.
you can use smaller buffer sizes here to actually minimize latency. And in terms of delay, if it's the human ear perceives frequency and delay at a particular time interval. So anything that takes longer than 10 milliseconds is perceived as a delay. If I play a pulse train, with 10 millisecond intervals, it sounds like pulses. You go lower than that, and it sounds like frequency. So it sounds, it's so, right. Right, so if the latency between you plucking the string and hearing it is more than 10 to 50 milliseconds, it will throw you off because you perceive it as delay. And I really don't know what it is for the flow graph that I put together. It's something, it's future work.
Hey, do you mind if I throw your repo up on PyBombs?
Not at all.
Okay, then give me 30 minutes and everyone can PyBombs that repo.
Awesome.
Do we have any more questions? I've lost track of time.
I think I'm still on time. Oh,
We have the-
I started late.
I know. I'm not.
That's my excuse.
So given that no more questions, let's go ahead and thank our speaker again.
Thank you.